For 40 years we thought falling into a black hole was terrifying but predictable. You stretch, you tear apart, you vanish. End of story. But on a Thursday afternoon in 2012, a group of 4 physicists sat around a table at the University of California, Santa Barbara, and what they discovered shattered that story completely. Because falling into a black hole, it turns out, is far stranger than we ever imagined. Stranger than spaghettification. Stranger than being crushed into nothing. Stranger even than the possibility that you might not fall in at all, because according to the latest research, the very latest from papers published in 2025 and 2026, the answer to what happens when you cross that point of no return might not be one answer at all. It might be 3. And they all contradict each other. Let us start with what we thought we knew. In 1915, Einstein gave us general relativity, and with it came the first real picture of a black hole, a region of space where gravity is so violent that not even light can escape. At its center, a singularity, a point where the math of physics simply stops working, where density becomes infinite and the laws of nature fall silent. Surrounding that singularity is the event horizon, the point of no return. For most of the 20th century, the story of what happens when you fall in was built entirely on this picture, and that story, the classical story, plays out like a cosmic horror film. Imagine you are an astronaut. You have volunteered for the most extreme experiment in human history. Your ship, the Event Horizon, drifts toward a stellar mass black hole, about 10 times the mass of our Sun. You are falling feet first. And the moment you cross the threshold, the universe begins to tear you apart. The force of gravity at your feet, closer to the black hole, becomes significantly stronger than the gravity at your head. The difference stretches your body along its length while compressing you from the sides. Physicists have a name for this process, borrowed from Italian cooking. They call it spaghettification. Think of it like pulling taffy. The material stretches thinner and thinner the more force you apply. Except instead of sugar and butter, the material being stretched is your spine, your organs, your very atoms. Within seconds you are drawn into a stream of particles, each one accelerating toward the singularity at nearly the speed of light. To an outside observer, you never even reach the horizon. Time dilation, another consequence of Einstein's equations, makes you appear to slow down, freeze, fade to red, and eventually disappear, as if the universe itself refuses to witness what happens next. This was the complete story for decades. Clean, terrifying, settled, but something was missing. In 1974, a young physicist named Stephen Hawking stood before his colleagues and dropped a bomb into the middle of that settled story. He asked a simple question. What happens when you apply quantum mechanics to a black hole? General relativity handles the big, stars, galaxies, the curvature of space-time itself. Quantum mechanics handles the small, particles, fields, the probabilistic dance of the subatomic world. The two theories have never gotten along, and nowhere does that tension become more explosive than at the event horizon of a black hole. Hawking's calculation showed something remarkable. Black holes are not truly black. They emit radiation, a faint, ghostly glow that slowly drains their mass. Over trillions of years, even the largest black holes evaporate completely. This is Hawking radiation, and it created a problem so deep that physicists are still fighting about it today. Here is the problem, in the simplest terms possible. Imagine you write a letter. You seal it in an envelope. Then you throw that envelope into a fire. The paper burns. The ink vaporizes. the letter is gone. But according to quantum mechanics, specifically a principle called unitarity, the information contained in that letter is never truly destroyed. In theory, if you could track every photon released by the fire, every wisp of smoke, every atom of ash, you could reconstruct the letter. The information is scrambled beyond recognition, but it still exists. Now replace the letter with an astronaut. Replace the fire with a black hole. Hawking's original calculation suggested that when a black hole evaporates, the radiation it releases is completely random. It contains no information about what fell in. The astronaut, the ship, the atoms, everything that crossed the event horizon is erased from existence. Not scrambled, not hidden, erased. This violates the fundamental laws of quantum mechanics. It is not just a minor contradiction. It is a declaration of war between the two most successful theories in the history of physics. Physicists gave this war a name, the black hole information paradox, and for nearly 40 years they fought over it without a clear winner. But then came that Thursday in 2012. The four physicists, Ahmed Al-Mhairi, Donald Marolf, Joseph Polchinski, and James Sully, sat down to settle the paradox once and for all. Their weapon was a principle called complementarity, an earlier proposal that tried to have it both ways. The idea was that what an outside observer sees and what a falling astronaut experiences are two complementary descriptions of the same reality. Both are valid. They simply cannot be compared. The team ran the math, and what they found made them stop. Complementarity did not work. At least not without introducing something far more disturbing. If the information that falls into a black hole eventually escapes through Hawking radiation, as quantum mechanics demands, and if an astronaut crossing the event horizon experiences nothing unusual, as general relativity predicts, then the two descriptions contradict each other in a way that cannot be resolved. The only way out, the AMPS team argued, is that the event horizon cannot be a gentle boundary at all. Instead, they proposed something violent, a seething wall of ultra-high energy particles, a firewall that incinerates anything attempting to cross. No spaghettification, no slow descent, just instant, total annihilation at the boundary itself. Think of it this way. If the classical picture of a black hole is like diving into a dark ocean, the firewall picture is like discovering that the surface of that ocean is solid concrete. You do not sink. You do not drown. You simply stop existing on contact. The paper hit the physics community like a thunderclap. It came to be known as the firewall paradox, or more dramatically, the black hole wars. But before we go deeper, and it is about to get much stranger, a quick pause. If you are fascinated by the biggest unsolved mysteries of the universe, you are in the right place. On this channel, we explore the cosmos not just as a collection of facts, but as a living story, one that changes every time we look closer. So, if a black hole can hold secrets that break the laws of physics, what other mysteries are we missing? Subscribe to Cosmos and join us as we keep asking the questions that the universe does not want to answer. Now, what came after the firewall? Because the war was only just beginning. In the years following the AMPS paper, physicists split into camps. Some defended the firewall, others rejected it. But a small group, led by Juan Maldacena at the Institute for Advanced Study, decided to approach the problem from a completely different direction. What if the answer was not about firewalls or complementarity or anything happening at the horizon at all? What if the key to solving the paradox was hidden in the relationship between the inside and the outside of the black hole? In 2019, Maldacena and his collaborators unveiled what they called the island formula. The idea is stunning in its simplicity. Inside a black hole, there exists a region, an island, where the rules of quantum mechanics and gravity stitch together in an entirely new way. Information that falls into the black hole is not destroyed. It is not even scrambled. It is encoded in this island region and eventually leaks out through Hawking radiation, fully intact, fully recoverable. The math is extraordinarily complex. The visual is easier. Imagine the black hole as a locked room. Information falls in and the door slams shut. The classical view says the information is gone forever. The Hawking view says the room eventually burns down, but the ashes contain nothing useful. The island formula says something stranger. The information was never actually trapped inside in the first place. The room has a hidden window, and given enough time, every letter you threw through that window floats back out. This was a breakthrough, but it came with a catch. The island formula works beautifully in theoretical universes, specifically in what physicists call anti-de Sitter space, a universe with a defined boundary, like living inside a tin can. Our universe, as far as we can tell, has no such boundary. It is open, infinite, and applying the island formula to a universe like ours has proved to be one of the hardest challenges in modern physics. So where does that leave us today? Right now, the physics community is converging, slowly, painfully, thrillingly, toward a resolution that none of the original combatants expected. The best understanding today is that all three pictures might be correct. Not in sequence, not as alternatives, but as different sides of the same deeper reality. To an outside observer, the astronaut never crosses the horizon. She is smeared across its surface, her information encoded in a holographic quantum state that will eventually emerge through Hawking radiation. To the astronaut herself, she crosses the horizon smoothly. She experiences no firewall, no sudden annihilation. She continues falling, the universe distorting around her like a funhouse mirror, until spaghettification tears her into fundamental particles. And from the perspective of the black hole itself, if such a perspective can even be said to exist, the astronaut's information was never inside and never outside. It was always encoded at the boundary between the two, in the island region, waiting to be released. 3 answers, all true, all incompatible in the language we use to describe reality. This is the state of black hole physics in 2026. We have not solved the paradox, but we have learned something perhaps more important, that the paradox itself is not a bug in our theories, it is a feature. It is telling us that the way we divide the world into inside and outside, into quantum and gravity, into observer and observed, is too simple. Falling into a black hole is not just a physical journey. It is a journey beyond the limits of how we think about reality itself. And if you think that sounds like philosophy dressed up as physics, well, you are not wrong, but that is exactly where the universe has brought us. Now, after a century of chasing black holes through telescopes, through equations, through wars of ideas and islands and firewalls, we have arrived at a place where the question is no longer just what happens when you fall in. It is whether what happens is a question the universe allows us to ask at all. We are living through the greatest era of discovery in the history of astronomy. New telescopes are coming online. New theories are being proposed. And the biggest questions about black holes, about the universe, about our place in all of it, are closer to being answered than ever before. If you want to go deeper, download the free guide and subscribe. See you in the next one.